Tech University, who is Associate Professor of Natural Hazards. He's working on very, very interdisciplinary research that is looking at sedimentology, coastal engineering, oceanography, and all of his work is applying all these diverse methodologies ranging from field surveys and laboratory analysis to numerical modeling, and particularly looking at the physical environment's response to extreme high energy events. So we're talking about tsunamis, we're talking about meteorite impacts, we're talking about storms, anything that has the potential for moving and perhaps depositing and leaving a sediment deposit on the landscape. So his work is bringing together an understanding of what the potential transport of sediments are and how it moves, and everything from the smallest particles to boulders larger than I am. Not so much larger, I'm pretty big, but this work is a really, really critical bridge because it's bringing together, for those of us working in the field and seeing deposits, being able to back model and reconstruct how it is that they got to where they are. So Professor Weiss will insist that he's primarily a computational and modeling researcher, and that he likes to spend his time in a closed room with a computer. However, you'll notice that he has done work in the field worldwide, including Chile, Alaska, Japan, India, Kenya, Thailand, to name a few. And now we've managed to bring him to Israel to add that to his list. So he's here as part of a Ministry of Energy, funded by the Ministry of Energy and Water. And he's going to be part of a project that I'm a collaborator with him, taking the field data that we have in Israel and applying the computational models and trying to use this information to better inform these models and vice versa. So we'll be advertising shortly. If anyone thinks of students, it can be almost at any level, first degree, someone finishing their first degree, master's, or going to a PhD or even postdoc, that might be interested in this field. We are going to be looking for someone to add to the project. Okay, so please, Robert.
Well, thanks very much, Beverly, for the introduction. I would describe myself as a theoretician, and I'm drawn to the field by necessity because of sometimes these tsunamis happen actually in the field and not just in my computer. And it's really important for me to go to the field to see the effects, not only to see the effects, but also see how difficult it is to do field work. And you notice that I have a sunburn in my nose because Beverly dragged me to the field, I would say, yesterday to Caesarea to look at her sort of second office that he has there. Today we're going to have a very simple outline, if you will. I will show you a few things that we've been doing in my group. Then I will talk about numerical simulations and what we can expect from them. And then we will talk about flow inversions from deposits. And we go from very small pieces of sand to very large boulders and look at different physics that is involved in their transport. And I can tell you what the outcome of this, or what I want to get across, the message that I want to get across is very simple. I want to get across that theoreticians or modeling researchers need to work closer together with those who do field research in order to narrow the gap or close the gap, because that's the only way to make significant progress in the future and prevent people from dying in natural hazards. So I hope with my short presentation I can convince you of that. Oops. The different things I do in my group are fairly diverse. It's all computational in the sense that we use fairly heavy computer equipment to do that. This is, for example, the work of my recently graduated student Roberto. He did in this modeling. He did a very canonical problem, which is the long wave propagation and long wave run-up in the lab. It's a wave tank that's about 3 times the size of this room, length of this room. And in the 80s, Kostas Sinolakis did these experiments, and he found out that if you zoom in here, that the shoreline, if you look careful, so 0 is the 0 is the shoreline. This is x. 0 is the shoreline. This is time. So, and what this line represents is the tracked wavefront. And you see here the wave approaches the shoreline, and then if you look careful, you see how the wave sort of makes a notch here and then goes up to the maximum run-up and then retreats back. And this acceleration here at the shoreline is very interesting because it only occurs at the shoreline. And at the time, it was sort of like it's actually very badly understood why this occurs. And we are speculating that, for example, there are such things as vorticity, which is a rotating effect of the fluid, and that vorticity occurs in different planes, and there might be a transition from one plane to another during that braking process or interaction with the shoreline that generates this acceleration. So if you think about an accelerating shoreline, and very simply considering Newton's second law of motion, F equals ma, and a mass that the shoreline has is accelerating, then the force is increasing in that area, and it's important to know where exactly that occurs and how strong the force is. And he essentially did that analysis and found out that actually the force is not a good measure of doing that, but the momentum flux. So the mass times velocity, and velocity changes. And that is done on graphic cards. So we used actually PCs or computers that were mostly built for gaming to do that. It was kind of interesting to write that budget to the university. They looked at me like, okay. And they had to ensure that the students actually don't play with it. And this is the same model. And here we looked at, this is Amir's work, also graduated now. And we looked at boulder transport by long waves. And we will talk a bit about boulder transport later in a more simple way. But essentially, boulders are very large objects. And we think that they only can be transported by high energy events such as storms and tsunamis. And there's always the question, in many coastlines on this planet, tsunamis and storms are competing processes for coastal change, and so it would be good to actually be able to separate these two from each other. And so we were speculating that maybe because of the difference in the waves, in the wave characteristics between boulders, between tsunamis and storms, that maybe in the characteristics of the transport, how they're moved in a three-dimensional space, there might be some characteristics in there that help us to distinguish between these two causative processes of boulder transport. Well, so we did a parameter study, and it's shown here on the right. So we have alpha is the slope, then beta is some other parameter, submergence, and then Fr is the Froude number, which is the velocity divided by the phase speed, essentially. And we see that there is no clear separation between different wavelengths in here. So this is what we call the parameter space. And the parameter space looks really complicated. I mean, we hope that there would be two blobs or something like that, or some simple geometry like a line, or some simple geometry that we can use to describe. If you think about this in 3 dimensions, which it is, then it becomes a really difficult to imagine geometric body, and that's usually, it's thought, at least in my world, it's thought to be a system that is not well understood in this. So we need to do a lot more research in order to do that, to understand better. And then Amir also did some other work, and that is with coastal vegetation. We looked into how, for example, coastal forests can maybe dissipate some of the energy of a long wave, of a tsunami. And on the right side up here, you see experiments. We actually got to play with real waves this time. So we took PVC pipes, glued them onto sort of a platform, and put the platform on a slope. We varied the density between the PVC pipes. You can see the PVC pipes here in this image. And then we ran waves through it, video recorded them, did some analysis from that, but also did some measurements of the waves, which are shown here. Different H is the thickness of the water column in this case. And then he was going and did some modeling on this. So, and this is the modeling result, and you can see how the red dots represent the PVC pipes in this case, and you see that the dots here as we go down in this direction, become denser. So traditional, and you see how that affects essentially the run-up. So this line here would be the maximum run-up. But you also see something very interesting. There's no vegetation here. There's very loose vegetation. There's a little denser vegetation, and there's a lot. The density is very high here. But you see that the maximum run-up doesn't change anymore between these two densities. So there might be an optimum density that we can apply in coastal engineering that can help to protect a specific case the best without, putting essentially a seawall of forest in front of you. And that's specific to a certain a situation with slope and expected waves. But actually, why I'm showing you this is not because of that effect. That's a side effect. Actually, the cool thing is, if this modeling is usually what we do in these cases, we describe the patches by different Manning coefficient. The Manning coefficient represents roughness, how rough something is. If we have on this floor, for example, if I take something and slide it across this surface, it's very easy to do because the friction between the body that I want to slide and the surface is really low. So Manning's N, the roughness coefficient, is very low. If I do the same on the carpet here, it will be very different. I have to use a lot of force to do that. That Manning's roughness is really high compared to that one. And that's the same for these patches. If I have a high Manning's coefficient, high roughness, that means that the flow in this area gets slowed down. If we increase this, then it gets slowed down more. But the problem with this is you have to find the right number to describe that most realistically, and I don't like that. So what we actually did is we resolved these individual cylinders as boundaries, and actually had the flow go through that, and we see the same effect of damping if we actually do that. So the grit that we apply becomes so fine that the water can actually go through these things. And that is computationally very tricky and very cool actually to see. And then here you see the effects of it. In this case, we have the axis h, the axis height behind these patches, and we can see that there are differences. Blue means that the height is lower than the case without any patch. And red means the wave height is higher than compared to without patch. It's very simple. So you can see here that there are certain structures that are almost coherent in the system that we need to better understand. And it's not a given that the water depth is always lower behind a patch. Sometimes it's actually higher, and that's an important information. And then we actually also did some work in Israel along the Israeli coast. In collaboration with Beverly, and where we looked at 3 different tsunami sources. One was an earthquake, and it's shown here in the red. The earthquake was somewhere in the Hellenic Arc, an 8.5, sort of like a biggish earthquake for that area. The other one in green are there are some very, very relatively large landslides in offshore Gaza, and we use that source. And then the blue line is a volcanic eruption, and essentially we use Thera for that. And you can see here which one is the obvious larger one, but the largest one. But interestingly, in this area here, where the landslides occur, they are in the same order. So whereas further away, it's pretty clear that earthquakes are the dominating tsunami hazard, or providing the dominating tsunami hazard, whereas where we have large landslides, then we actually have to look more careful and analyze that more carefully to actually say what provides the bigger threat in terms of tsunamis. And then there's my student Hui, who also just graduated, as you can imagine now, free of students, which is good and bad. That means I can do whatever I want. He created a model that we call STRIKE, and that stands for Sediment Transport and Coastal Hazards Events. And that is based on, we used here GeoClaw, but it's a long wave model. But it's essentially a standalone sediment transport model that is tuned to consider sediment concentrations that are very large in the water column. Traditional sediment transport models usually assume that the sediment concentration is less than 3%. And that's actually a lot, given that sediment is usually 2 to 3 times heavier than water. But actually, during coastal hazards event, if you remember the pictures that were online or on the television from the Japan tsunami, there was this famous picture where you had the seawall and the water just overtopped it, and it was black water or really brown water. That's not the density of 1,000. That's probably a density closer to 2,000, and that's if you m is equals ma. M being the mass, volume times density, is a bit different in terms of force. And that's something we need to include in our hazard assessment, which we haven't done. The model performs really well in this situation. We have recently coupled it with a different model for better performance. But essentially, we are able now to simulate actually the movement of sediment on with a lot of computational, with the relatively high computational efficiency. All right, so much to my students, and now I can show for the rest of the time. I'm going to show you what I'm sort of do, the almost dinky little work that I do compared to the students that I have who are very, very smart, and I was very honored to be their advisor. But before we're going to do that, I would like to talk about expectations of numerical modeling. And that's the question, what are they good for and what are they not good for, what they can and what they can't do. And of course, as a geophysicist, we try to figure out what is happening on our planet. And as we know, our planet is complex and unique in the solar system, and that makes it really difficult to actually simulate processes on the Earth reliably. Based on our limited physical understanding, but also on our limited data that we can collect about the planet. So we need a model for the model, if you will, and I'm going to introduce you to the best model that I've found. No, that's not the model. That's the model. The Mona Lisa. And it's fairly simple. Mona Lisa is, in this case, a model. It's the Earth. So we want to understand and recreate Mona Lisa, the Earth. So you can look up, you can go on the internet, and you can find ways to recreate that. So you can go and you find a recipe, an algorithm, how to recreate Mona Lisa. And you can see here how this is done with the circles and the geometrical lines and so forth. It also gives you how you hold your hand, what pencils to use, or brushes. It's really cool. I mean, it's really amazing. And in the end, this artist did a reasonably good job. There are some differences. It's not exact. But the main features of the Mona Lisa are there. The smile, yes. The face, cool. It's really similar. It's not the same, but maybe this artist really understands now what it takes to draw a Mona Lisa. Despite the fact that I did that, it still come up with this. So I really don't. But yet I learned something very, very important. I understand now what it takes to draw the Mona Lisa, and I can tell you I cannot. I'm much more familiar with other things. So, and the reason why we need to do this is very simple, because it's not only to increase our understanding of the globe, it's very practical. This is a map of the United States, and I'm sorry for that, of nuclear power plants. There are 350 of them. And the majority of them is near a water body because of nuclear power plants needs water, and then they are prone to tsunamis. We need to really understand what are they facing. In the east coast of the United States, there are 110 known submarine landslides on the continental shelf. Completely unknown when they occurred and what kind of hazards they pose at the moment. We have a similar situation, for example, at least from the landside perspective in Gaza. The other thing is maybe less traumatic than a nuclear problem that we had, for example, after the 2011 tsunami in Fukushima are the cables, the data cables that are in our deep oceans. So, for example, in the 1920s, there was the Newfoundland landslide and tsunami. That took out the communication cables between the U.S. and Europe, and that caused big trouble. So here are all the cables, and that's 2009. I couldn't find a map today, so I maybe zoom in here. So we have a few in this area too. So, and there are lots of them, and they have to come out at the coast somehow. And these cables are under threat by tsunamis and landslides. And it's not just the inconvenience that we will face when these cables fail, that we don't have internet. It's actually really serious, because of trillions of dollars per day move through these cables. And when they're interrupted, then how are you going to do international bank transfers on a large scale? And that is something that most people are worried about. Or how do nations communicate with each other about certain immediate important situations if communications is limited at the time. So these are the motivations that we need to have in order to figure out, or to also be aware that we need to communicate as geoscientists with the respective authorities that the work is important indeed, and it cannot be engineered. Anyway, we were here. I cannot draw Mona Lisa, but nonetheless, I believe I learned something, and it's a good model for the Earth. Now you can think about what I think about how I think about the Earth, given the model. So tsunamis and storms are actually kind of rare, even though since 2004 we have about every couple of months a tsunami in the news. They actually occur quite frequently. I used to develop, or I was part of a team that developed the tsunami warning system in the Pacific, and I'm still getting the emails, when an alarm goes off and the buoys go on, and it happens actually almost every week. I mean, like, there's just small and nothing to worry about, and we're always happy that they don't hit the news because it's unneeded attention to this problem. But yet, tsunamis in any given region of the planet are rare. So that also means that we cannot use the few tsunamis that impact a certain region from the historical record or measured record to calculate or estimate a recurrence interval, and therefore a hazard assessment and a risk assessment. We need to use the only thing that we have from old events, and that's the sedimentary record. So we need to interrogate the geological record and archaeological record of tsunamis in order to find out what is, in any given region, the hazard that we face. And that's the sediments, and we want to use the entire spectrum of sedimentary deposits from very small to very large. And right now I can tell you they're not integrated at all with each other, but in the future we would like to have that integrated. So I'm going to talk first about boulders. And boulders can anything. This is a boulder. It's about the size of my hand. And this is a boulder. So this is a meter here. So 1, 2, 3, 4 meters and 20. So it's probably almost twice as large as this room. And both of these particles were moved by a tsunami, by very different tsunamis. As you can imagine, you need a very small, relatively small wave height to move these boulders, and you need a very large tsunami to move this boulder. Maybe. Or is it possible that it was moved by a storm? Can we say from this picture? Probably not. So we need to understand the physics of boulder transport in order to figure that out. And we're going to do that. So we're going to use very simple physics. And this is the world. This is the view of my world. They are all full of circles and spheres and simplified situations. But I learn a lot from these simplified situations. So the theoretical framework we're going to use is drawn here. This is our boulder, and it's a circle or sphere, which is obviously not at all realistic. And it is on a slope, and there's a roughness element in front of it. And to dislodge the boulder, to move the boulder has to move from this position. This is the same position in the dashed line here, to this position in order to move down. If the boulder doesn't reach this, it will fall back into its original position. That's an important situation. Imagine you have 3 balls in your hand, and you put a fourth ball on the top, sort of like a pyramid, and then you want to roll this ball out, and you just roll it a little bit, and you let go, and it falls back into the pocket. If you roll it out a little more, and you let go, it will fall back into the pocket. If you roll it on top of one of the balls, and just a little beyond, it will roll down. So that's this critical angle of dislodgement that we see in there. And that needs to, and the driving forces, for example, the waves or the fluid flow, need to move the boulder to that position in order for the boulder to dislodge. And very simple in this way, what we used to do, or what we usually do, we take the sum of the forces, larger than 0, will make the boulder move. The sum of the forces means the drag, the lift, and the counter forces are the weight, and so forth. That's not enough, because we not only have to move the boulder to see if they're dislodged, they have to move it to the boulder has to be moved to a certain point, depending on the situation, how they're located, to dislodge. Because only if they're dislodged, we can see if they're moved or not. If that guy moves back into original position, how can we identify in the field that thing moved? We cannot. So we need to use a little bit of equations here to explain how we're going to get there. So we're going to use a very simple equation. Actually, I argue that this is the most difficult equation that you will ever see in the making. You cannot deal with this equation because it's super complicated, even though it looks very simple. So the first thing we do is, because we saw here this is a rotation, we can transfer the coordinate system to make it simpler. So I use the cylindrical coordinate system, and that makes the equation simplified to this. Theta is the angle of rotation. R is constant, so it's pretty trivial. On the left side now, essentially the mass would change into this form. The reason for that is the boulder is submerged in water. And the boulder, when it moves, has to displace water around it. So, and that is given in this, and that's taken care of in this formulation here. Then the sum of the forces is the drag, the lift and buoyancy, and the weight. That's the standard simplified way. We call this the quadratic representation of boulders because they all depend on the square root. These and L depend on the square of the velocities that we're going to have. So this is a fairly simple model if you put it together. It's super simple, and it's theoretical, so this doesn't have really practical. But again, to demonstrate this framework again, so this is the situation where the sum of the forces here is less than 0, theta is 0, its initial position. Delta, the roughness, is given us 1. And as you can see, I define delta as a function of r. So delta 1 means that it's exactly the radius. So what is the prediction if you think about what angle, how much do we have to move in order to move the boulder? So we have to move this angle, and that's in this case a right angle. If we change this r, if we change this delta to here, then this angle will change as a function of r. So very simple. Let's move forward. So here we start the motion starts. The boulder starts to move because the sum of the forces is larger than 0. The boulder starts to lift up, rotate around this point here. And then what we can see here is that the angle, theta, is larger than 0, but smaller than the critical angle of dislodgement in this case. So we're rotating out. And we continue this, and we continue this. And if, for example, the forces would stop now, you would cease the forces. So you would make this go to 0, or negative actually, then the boulder would do what? It will move back, because of the angle is still smaller than the angle, the critical angle of dislodgement. And that is actually a reality. If you think about a wave comes, has this maximum and goes. So if the wave has a large amplitude, the boulder will start to move. But if that wave is not long enough for the boulder to move all the way up here, then it will go back. And we never see as to whether the boulder has moved or not in the field. So we continue that, and at some point, it reaches to the dislodgement point, and then from there onwards, it will dislodge, move, and we can see that the boulder has moved. So the theoretical concept that this is borrowed from is from what we call the impulse theory of dislodgement. So instead of using the shear stress as an indicator or some sort of flow and mass composition in sediment transport, we often use the critical shear stress. You may be familiar with Shear's equations or Shear's law or Shear's parameter. That uses simply the shear stress, the critical shear stress. That's the amount of shear stress I need or exert on a grain for it to move. If you do that for these very large particles, it turns out that's not right, because it has to overcome this very large roughness. So, and if you actually look at the impulse as the integral over time, the force over time, we actually can see that we need to exceed a certain critical impulse in order to do that, and we can calculate that with the respective theory and so forth. And actually, I'm working on with Panos Diplos, who invented this. He observed this in the laboratory and derived the respective theory for actually looking at real bed load transport of smaller cranes, and it works quite well. So the other component that we have to have now is we know how the boulder moves. Now we have to provide the forces for it to move. So we need to look at the velocities. And you could go ahead and use, like, say, a sine function like I have in the past, a sine function to describe a wave that would look something like this. You know, you have your wave here, and we would call this, I would call this now a monochromatic wave, which it is. But if you look actually at nature, monochromatic waves don't actually exist in nature. In very, very special circumstances, but definitely not during a storm. There are many frequencies involved in a storm, and even more so, there's a lot of interaction with bathymetry in the different components. The different spectral components interact with each other and form very, very complicated situations. And that's what we have to take into account. And that's what we do when we in this sort of method to calculate the forces or the velocity. We're actually going to use a spectral model, and we're going to represent what we're going to look at as a spectrum. Therefore, calculate different realizations of the same initial spectrum that we can then put together under the umbrella of waves as random processes. Because that's what they are. If you measure the same waves twice in a row, or you do it for a long time, then you see a repeating pattern, whereas you are unable to predict an exact state. It's kind of interesting. It's sort of a cool thing. And if we do that with the Triads model, and Triads uses Triads wave, which is the interaction of three different waves, and it's sort of written down here. And the model domain is fairly simple. We have a sloping beach, which doesn't exist obviously in nature, but for the sake of simplicity, sloping beach, 20 meters on the right, 0 meters on the left. In this area here, the model is forced with this Jean swap spectrum, and then it will run 100 realizations of the same model of the same spectrum ashore. So what it does is we have the spectrum, but we don't know in what order the different components of the spectrum come in. And we create 100 scenarios with 100 random phase shifts between the spectrum and let that go through. So we have 100 realizations of the same spectrum. So when we do that, and what you see here is the spectrum at different water depths that we calculate. You see a slightly sort of gray shaded area. That's the minimum and the maximum of the energy that we see, the spectral power, the spectral density. And the red line in this area, in these three plots, represents the mean of it. So that's the beauty of this is now you can do it statistically. You can use some a description of the spectra to do that. So, or to describe the system. So what do you see when you look carefully in this graph? You see a few things. We have at the in smaller water depth the range here that the different spectra is very narrow, and as we go towards shallow water, the range in this area becomes wider and wider and wider. That's kind of weird. But also what you see is at about this stage here, and these lines are always the same. If you draw a line here, the amount of energy that is in this area here is larger and larger and larger as we move towards the shore. And the wavelengths associated with this are given down here. It's given in frequency, so smaller numbers means larger periods. So that means what? It means more and more energy as we go from from deep to shallow water is pushed into longer wavelength, and we call that infragravity. This band is called infragravity waveband. So we increase the energy that is in infragravity in the infragravity spectrum. And you see here the numbers. We see here that forget the numbers, but the exponents. We increase by moving from 20 to 5 meters of water depth. Given this example of initial spectrum, we have 2 orders of magnitude increase in the infragravity component, meaning that we have longer wavelengths in the spectrum where the boulder is transported, meaning that the forces can be exceeded for longer periods of time that may or may not generate into the dislodgement of boulders. And that's the cool thing about that model, in my humble opinion. Okay, so what other effects does that have actually on the time series that we can observe? Again, this is A, B, and C represents 20, 15, and 5 meters of water depth. And you see here just randomly picked 3 different realizations out of the 100. And you see here that they're relatively difficult to distinguish if you use just the whole time series here from 0 to 600 seconds. You can see still a few things even here. You see here that I want to point out that even here in this plot you see already that you have spikes. They're relatively small, but they are symmetric, more or less symmetric. You have crests that are as deep as troughs. And as you go from to shallower water, you see you have more spikes all of a sudden in there. So you can create a few situations where you have really high wave heights, depending on how they interact with each other. If these waves interact constructively, building up wavelength, or destructively, where they diminish wavelengths at this particular spot. And then what you also see in shallow water, that you have an asymmetry between the wave crest and the wave trough. They're no longer the same. So monochromatic waves where you have to have the same trough and the crest, that model doesn't work anymore, at least in shallow water. If you zoom in a little more here, and this is the same 20, 15, 5, and we zoom in between 50 and 100, and you can see how this over here all of a sudden, this realization has a huge peak, a huge trough, whereas the other ones do not. So could the boulder be moved? Or here, could the boulder be moved in there? Yes or no? We don't know, but we can check out. So what we're going to do is we're going to use every of this 100 realization and run it with the boulder transport model, couple it with the boulder transport model, and then count how many for any given condition, any given initial spectrum, how many of those realizations result in boulder dislodgement compared to the total of 100. So very simple. And the most important parameter is mass of the boulder and roughness in front of the boulder. That's what we just said. You have a question?
Doesn't the roughness change during the wave?
We just use geometry as a roughness. You mean how much fluid is around the
Also, the wave changes the front of the wave.
Yeah, we don't. Yeah, I know what you mean. Yeah, that's too that in this simple framework it's too difficult to put in. We can have that in the three-dimensional things I showed earlier. We have that in, but we found out it's actually not that difficult. It's like the 80-20 kind of. We can go back to it later if you like. So we change the mass, and we see that if the boulder is relatively light, then we have almost all of the realizations cause boulder transport or dislodgement. And as we increase the mass in this way, the boulder, we call the frequency of boulder dislodgement will go and eventually go to zero. Note here, though, that this is in log scale. So there's a wide variety of boulder masses that can be transported at different frequencies. So we can do that for one boulder. We can do this for one boulder, or we can do that for many boulders. And this plot, and this is where the computational people at my university started to hate me. This is 60 million model runs, sort of coalesced in one picture. And that is really cool because you can see very intuitively I should zoom in on here. Maybe let me zoom in this one. So what you see here is the first number is the significant wave height offshore at the model start, and this is the respective period. And you see here we go. So you see 2 meters, 2 meters, 2 meters. This is the 4 meter, 6 meter, and 8 meter significant wave height. And then we go from 8, 10, 12, 14, 16 peak periods. And so you see that the larger the wave, so this is a small wave, this is the biggest wave, so we go big and big. And if you do that, you see that the masses are increasing, giving here in the colors, blue means 0, red means 100, or close to 100, that the masses increase. So it's very intuitive, right? But we need to go further, actually. That's great, and it's intuitive, but it doesn't give us anything. So to actually make use of the 60 million model runs, I thought, well, let's start looking into some other things, for example, tsunamis versus storms. So this is roughness again. This is mass. And what you see here, the ratio D in this case is the ratio of the amplitude of the waves that is between a storm wave and a tsunami wave in this parameter space. And different planes are different angles. And you see here that it's actually, if you look here, we have from 0 to 0.6 to 0.12. The changes are so small that I come to the conclusion that we actually cannot distinguish between boulders moved by storms and tsunamis, because the wave height that you actually need on various, for my taste, too similar to say anything specific. Anyway, now we're going to use the 60 million model runs, which I'm so proud of, and my university not, to do something meaningful with it. And so let's for one angle, let's put them all together and try to do a dimensional analysis on them. So X now is the grain size, the boulder size. S is the significant wave height, and L naught is the initial wavelength that is related to the peak period of the spectra, of the input spectra. And that's plotted against the frequency of dislodgement. We see a similar line here. So we can describe this line with this function, which is based on the Q function, sort of an arrow function type sort of situation. And if you do a little bit of analysis, you find out that the significant wave height is proportionate to square of the grain size, and so forth, and it's inverse proportional to the angle. If you involve actually a different set of equations, you actually find out that it's two-third or something to something else, which I cannot for the heck remember right now, and that makes me really worried, because that means it's very sensitive to small changes. If you have fractions or even this high, even squares, something that's not 1 makes me worried about the whole thing. So how much time do I have? In 2. Okay, then buckle up. We're going to increase the speed. Okay, so now we're going to sand. So the reason why what I'm concerned about sand is we usually use sediment transport paradigms that sort of look like this. Clear water, a little bit of sand. That looks beautiful in itself, but it's not realistic. What we actually see is this. The thing is full of sand. And that changes the equations that we need to use to consider this problem. So we need to use a model that describes the distribution of sand or particles in the water column, which is given here. And then we have to translate this into a sedimentary record of it. And if we do that in a very simplified way, we can actually do it very fast and then inverse it, use it as an inverse model. And this is what we have done here. So we use a method called ENKF, in common filtering, that is heavily used in ensemble common filtering. It's heavily used in weather forecast, for example, and it's a data analytics or data analytics method. It's essentially to update or augment the state of a model and then rerun the model with new insights. It's part of a Bayesian statistics. It's part of Bayesian statistics. So the model learns as we run it, and we iteratively approach the truth or the best value, the best estimate for it as the model runs. It's really a cool thing. So first of all, this is without this in common filtering, and what you have to do is lucky guess initial conditions and parameters throughout the modeling to achieve a fit like this. So in red here we have data. In green we have simulation results. And if we translate this to thicknesses, again in red the results, and the measurements, and in green the results. But this takes some time to get the fit. It takes really a lot of time to get this right. And I feel uncomfortable with the situation when I have to play with a model to make results look right, whatever that means. Because I don't really know, especially if you go to a situation where you don't have data. That's actually the biggest advantage of models, that you can go into areas where you all of a sudden don't have data, but you have the trust in the model that you built up by comparison with data. And that's where the in-common filtering technique comes in, so we don't have to choose. And let's skip that. Yeah, we can talk about that later if time. Maybe that too. Oh, yeah, maybe let's talk about that. So we did that, and that also helps us to use this method, exactly what I just said, in areas where we don't have data. So, for example, in this case, it is actually for the Haiyan typhoon 2013, I think, in the Philippines, in one of these beaches. So what we did in this modeling is we took sediments that we have, and I think the sediments are shown here. Yeah, sediments are shown here. CA, the red, are the measurements, and this is our best fit that we could achieve with the model. There are certain reasons for that, why it's not good, because we had to ignore certain components of the grain size distribution, simply because the model cannot handle very, very large grain sizes. It's just impossible. There's a different physics involved. So based on that, we can calculate a minimum and a maximum velocity on the model and based on the in-common filtering technique. And then we can use that to extrapolate outwards towards the shoreline and do that in a very meaningful way. So without this technique, this would be completely hand-waving. I mean, I have no freaking clue I had no idea how it would work. So anyway, so this is just for one. For the previous example where we had to pick it, the velocity, minimum, max, and then the respective route number. And here we have it automatically computed and picked. Okay, so what I need to stress here is again that the input is a grain size distribution as well as the grain size thickness. So the interesting thing is, if you take out certain components of the grain size distribution, what do you have to do? You have to augment the thickness. And then but then how you do that? And that's another problem that we are facing right now, is how can we augment, or how can we change the model so we don't have to do that anymore? But these particles that we look here, -4, are rather large, but they cannot be described as a concentration because the concentration is so small, they need to be considered as particles, and then we have to solve Newton's second law of motion for each of them, and that might become too much of a hassle. So how we can combine this with field, and that's another advantage of the NKF method, is we can actually have an error model in there and quantify uncertainties. And the errors come from two things here, right? We have measurements, they come from measurements, and they come from the model itself. And then we can do a lot of things with that, but what is shown here is the measurement error. And we can invert for two different things when we do the inversion. We can invert for the flow depth, and we can invert for the flow velocity. And if we do that, we impact the error given on how many samples we have per sediment thickness. So the sample frequency is let's say you have a meter of sediment, and in this case you have between 5 and 30 samples from that meter. And you do it the same way there. If you invert for the flow depth, you see that the error sort of goes up and then down and then up and then sort of stays constant. And you have a similar situation for the velocity. It goes up or is up and then goes down and then goes up again. And that is probably because you have simply because you have so many samples now that you make a lot of mistakes weighing them, for example, or identifying individual grain sizes. But the interesting thing is you have a minimum in each of them. But the stupid thing is they occur at different locations. And I hate that. Because we can, so for example, in this case, you need 10 or 11 for H, for flow depths. And for this, you need less. So if you combine these two, maybe you end up at 10 or so. But then you sacrifice error for this. And it would be so nice if the things would behave as we want, so where we have the same error at the same time. But we also learned something very important in this, and I think that's my last second. We learned something very important in this too. If we would do the same error analysis with a model error, we would find the same thing. And so one of the conclusions we have is in this, if we have it doesn't make sense to have a very precise model and have crappy data. But it doesn't make sense in the same way to have very precise data and a crappy model. It turns out that you have to have very similar errors in both the data and the model. But then how do you quantify that? Or how do you do that? How do you make sure that you have a good model that is appropriate for the data that you collected? So, and what does that mean? If we have, we go, for example, Beverly takes this now and says, oh, we have to collect 10 samples. But in the past, she hasn't done that. Maybe she collected 1, maybe she collected 5. But how do we find the appropriate numerical model then to minimize the error of the inversion of this? And that is sort of something that I'm trying to understand now. This sort of error models, uncertainty quantification, error models is all linked to each other. And that is where I think where the biggest problems are, actually a really objective error analysis and uncertainty quantification. All right. With this, I want to conclude. And as I said before, tsunamis and storms are often competing agents of coastal destruction in this case. I think we need to move from process-oriented deterministic models to process-oriented or process-informed stochastic models because we need to move on to a more complex and realistic situation. I think modeling can really make a lot of progress if it includes field data and vice versa. Like we can now, with the previous slide, we can go out and say you need to take an n number of samples, otherwise you underinform our models, and it doesn't help. So that also means that if you are a student or a young researcher, you need to make a decision. And I get these emails a lot. Oh, I would like to be your grad student, and I would like to do some modeling, but also some field work. And I say, no, I'm sorry. You cannot do this anymore. This is beyond. You either become a really, really good field scientist, or you become a really, really good modeler. Unfortunately, for tsunamis and storms, because of the processes are so complex, you need to make a decision. You should learn about the other side. You should need to go. I go to the field a lot, and it's fun and hard sometimes. But it's also important because of it sort of trains my modeling effort. And it's the same the other way. Some modelers, I think there's a value in for field people to learn about modeling. It's not a bad thing. It's not magic. So it's learnable. And the last one, obviously, is sort of a self-serving thing. There's a lot of work to do, so that's always good to tell funding agencies so that they fund you. And with that, I thank you for your attention and invite questions.
Okay, thank you very much. I see that you have funded one question.
Okay, choose wisely.
Okay, so I will ask you
this might be a very long answer. I didn't quite understand how your modeling approach resolves the non-uniqueness of inverting sediment, the sediment record back into runoff velocities.
Oh, okay. So essentially, what we do is, it's actually super trivial. It's super trivial. So you have a sediment. You measure the sediment, and you have layers in there, and you see there are fine grains on the top, for example.
How do you solve the non-uniqueness?
I know. I'm trying to. It's actually super simple. It's not addressing this at all. It's essentially taking the sediment in the water column and let it settle out. So in a sense, it's a settling. It's through a settling process. So it's insanely simple. So there is no more complex consideration involved. We've done respective studies with a particle model where we had things moving, and we found out that's actually not that important to have because not important to have the horizontal component in since we can assume that it follows a Rouse profile, and it's actually
So you just reduce the order of complexity.
yes, it's very simple.